So even though Kepler's third law of planetary motion came before Newton's second law of motion, we can use Newton's second law of motion to derive Kepler's third law of planetary motion, as we'll do in this lecture. But first, let's begin by making the following two important assumptions. Assumption number one: the pathway of the planets around the sun is a perfect circle. And this is a good assumption because most pathways of the planets around the sun are very close to being circular, are very close to circles. So let's suppose we have the sun and we have the planet. We're making the assumption that the pathway the planet takes around the sun is a perfect circle, where this r is the radius of the orbit, this r is the distance between their center of masses. Now, the second assumption comes from the fact that the mass of the sun is much, much larger than the mass of the planet. And because the mass of the sun is much larger, the acceleration the sun will feel due to the planet will be very, very small. It will be negligible. And that means we can make the assumption that the sun in our system is stationary. So in this system, the sun is stationary and the only object that is moving is the planet. The planet is orbiting a stationary sun. So we begin by writing down our Newton's second law of motion given by the following equation. All the forces acting on our object, on the planet, is equal to the mass of that planet multiplied by the planet's acceleration. So the only force acting on the planet is the force of gravity due to the sun. The sun is pulling on our planet and it's accelerating the planet in the following circular motion. So we can rewrite the left side in the following manner. Our gravitational constant g multiplied by the mass of the planet multiplied by the mass of the sun divided by the radius of the orbit squared is equal to, well, the right side. And the right side can be written in the following manner. The mass remains the same, but acceleration can be rewritten in terms of velocity and our radius of the orbit. So v squared divided by r. So recall what the relationship is between velocity and period. Velocity is equal to the circumference of our orbit divided by our period. So we can take this value, this term, and substitute it into this equation for velocity. And we get the following. We see that the right or the left side, this side, is equal to the mass of the planet multiplied by 4 pi squared multiplied by r, because this top becomes r squared, the bottom is r, so 1r cancels, and we're left with r, and the bottom becomes the period t of the planet squared. So now we can rearrange this equation by bringing the period to the left side and the r to the left side, everything else to the right side. So the mass of the planet cancels out, and we see that we have the following ratio. The period of the planet squared divided by the radius of the orbit, or the distance between the center of masses of the two objects cubed, is equal to 4 pi squared divided by the gravitational constant multiplied by the mass of the sun. So notice this is in fact a ratio, and this ratio is always constant. So notice that this ratio that we found was derived for only one planet. Let's say we derived it for the planet Earth. Now the same steps can be followed to derive for a different planet. So let's suppose we take the same exact steps and derive another formula, the same exact formula, but for a different planet. Notice this ratio stays the same. So that means, let's suppose 1 is one planet and 2 is the second planet. We can equate them because the ratio is always constant. And this in fact is our equation known as Kepler's third law of planetary motion. So if we take this equation and we rearrange it, we get the following equation, which is exactly identical to Kepler's third law of motion. Now notice that this equation only works for planets or objects orbiting the same center. For example, I can use this equation to compare the orbit of Earth to the orbit of Mars or some other planet. But if I want to talk about the way the moon orbits the Earth and the way the moon orbits Jupiter, I cannot use this equation because the center of masses are different. For one, we have Jupiter, for the other, we have Earth. So this only works when the center of mass of our two planets or objects are exactly the same.